As a diabetic, I rely on a device like this quite a bit. It's called the glucometer, and it measures the level of glucose in your blood. You strive for a level of between 80 and 120. If it goes too low, you're in danger of going into a coma. And if it goes too high, all kinds of bad things can happen to you. So the glucometer is extremely important for diabetics. Now, how does it work? Well, you insert a little test strip into the device. Then you put the tip of the strip into a little drop of blood. Blood is pulled up the sides of the test strip via capillary action and contacts a glucose oxidized layer, a layer that oxidizes glucose and forms gluconic acid. Gluconic acid reacts with potassium ferrocyanide layer to form potassium ferrocyanide, which in turn reacts with the metals on the electrode layer, which causes an electric current to flow through the electrodes. The strength of this electric current is converted into a numerical reading of milligrams per deciliter of blood glucose. This technology relies on the science of electrochemistry, which we will be looking into in this chapter. So what is electrochemistry? Well, let's start with the beginnings that you should remember really from Chem 1A. What is oxidation state or oxidation number? It's the positive or negative electrical charge of a combined element stemming from a surplus or deficiency of electrons. The oxidation state of an element in an ionic compound is equal to its positive or negative charge. So what's the oxidation state of sodium in sodium chloride? Duh, +1. What's the oxidation state of sodium in sodium sulfide, Na2S? Well, it's still +1. What's the oxidation state of aluminum and aluminum sulfide? That's going to be a +3. And the oxidation state of sulfur in aluminum sulfide, that's going to be a -2. In covalently bonded species, you follow a few rules to determine oxidation number. Rule 1, the oxidation number of an uncombined element is 0. So if it's just an element in its elemental phase, then it's sodium or chlorine or P8. All have an oxidation number of 0. For rule 2, for a compound, the sum of all the oxidation numbers of the atoms of the compound is 0. For a polyatomic ion, the sum of the oxidation numbers of the elements of the ion is equal to the charge of the ion. Rule 4, the oxidation number of group 1 elements is always going to be +1. Sodium, lithium, potassium, etc. Hydrogen is usually +1 unless bonded to a less electronegative element, but we're not going to cover that in this course. The oxidation number of the 2A elements in compounds is always +2, calcium, magnesium, etc. And the oxidation number of fluorine in compounds is always -1. The other halogens are usually -1. And the oxidation number of oxygen in compounds is usually -2. Don't worry about the exceptions. So using these rules, what's the oxidation number of nitrogen in ammonia? Think about it. And if you chose -3, you are right. How'd you get it? Well, hydrogen is always +1, at least for our purposes. So if hydrogen is +1, there are 3 of them, that's +3. Nitrogen to balance has to be -3, so it adds up to 0. Here's another one. What's the oxidation number of nitrogen in N2O4? Think about it. Choose. All right, let's go through it. Oxygen is always -2. There are 4 of them. That's -8. So the nitrogen side has to be positive. There are 2 of them. And it has to add up totally to +8, because the oxygen side is -8. So +4 would be the oxidation number of nitrogen in dinitrogen tetroxide. You know, the guiding principle behind the rules and the previous slide is that all the electrons in the covalent bond are assumed to belong to the more electronegative element. Because oxygen is the second most electronegative element in the periodic table, we use its valence to come up with a -2 charge, just as if it were in an ionic compound, for the purposes of figuring out the oxidation state of the other element, like nitrogen in N2O4. Conversely, hydrogen is a very low electronegativity. It's usually going to be positive, and we use that understanding to figure out the oxidation state of the element that hydrogen's attached to. What's the oxidation number of nitrogen in the nitrate ion? All right, here we go. Oxygen is always -2 for our purposes. That's -2 times 3, or -6. The ion has a -1 charge, so the nitrogen has to be +5, such that you have +5 -6, giving a -1 charge to the nitrate. Answer, +5. How about this one? Oxidation number of chromium in potassium dichromate, K2Cr2O7. All right, here we go. Oxygen is -2. There are 7 of them. That is -14. Potassium is +1. There are 2 of them. That's +2. This whole thing has no charge on it, so all the oxidation numbers have to add up to 0. So we're at +2 and a -14. That's a -12. So the 2 chromiums together have to be +12, and there are 2 of them, so that makes each chromium +6. Find the oxidation number of all elements, both reagents and products, for the reaction of methane plus oxygen yield carbon dioxide and water. Okay, here we go. Hydrogen is +1. There are 4 of them. That's +4. Carbon has to be -4 over here. Oxygen is 0 when it's bonded to itself like that. Carbon dioxide, oxygen is always -2. There are 2 of them. That's -4. Carbon is +4. Notice that carbon has changed its oxidation number from a -4 to a +4. And water, of course, hydrogen is +1, oxygen is -2. So here's a summary of that last question. Methane, the carbon is -4 in its oxidation state, oxygen is 0. The oxygen in carbon dioxide is -2, and the oxygen in water is -2. And notice that carbon has gone, therefore, from -4 to +4, and the oxidation state of oxygen has gone from 0 to -2. So here's a couple of questions. Is carbon gaining or losing electrons? And is oxygen gaining or losing electrons? Okay, so remember that electrons are negative little buggers, so if something is becoming more positive, it's losing electrons. Carbon is losing electrons, and that's why its oxidation state is going from -4 to +4. On the other hand, oxygen is gaining electrons. It's going from 0 to -2. It's becoming more negative. Now, the process of losing electrons, the loss of electrons, is called oxidation. And the process of gaining electrons, we call that reduction. A loss of electrons is oxidation, a gain of electrons is reduction. There's a mnemonic that people use. Leo goes grr. Leo the lion, right? Leo goes grr. Loss of electrons is oxidation, gain of electrons is reduction. Another one I've heard is oil rig. Oxidation involves loss of electrons, that is. Reduction involves gain. Now, just to make things more interesting, there's another way to look at this, and that is to talk about a reducing agent and an oxidizing agent. An agent is something that acts on something else. So, carbon is in the process of being oxidized. It is undergoing oxidation, but it is also acting as a reducing agent for the oxygen. In the process of losing electrons, it is acting as an agent to cause reduction in the oxygen. And conversely, oxygen is undergoing reduction, therefore it's an oxidizing agent. It's acting as an agent to oxidize the carbon in methane. That which is oxidized is a reducing agent. That which is reduced is an oxidizing agent. So for the reaction of nitric acid and solid chromium metal, forming chromium ion plus 3 and nitric oxide in water, what is the species being oxidized? And I always like to go for the easy route before the more complicated route. So chromium as a solid metal is an oxidation number of 0, and chromium plus 3 is of course plus 3. So it's very easy to see that the chromium is being oxidized. It's becoming more positive because it's losing electrons. So there's your answer. Chromium is being oxidized. For this question, permanganate plus aluminum yields aluminum ion plus manganese plus 2. The question is asking for the oxidizing agent. Again, I go straight to the aluminum because I can easily see without any calculation that it's going from 0 to plus 3. That's oxidation. Therefore, it's the reducing agent. Therefore, the permanganate is the oxidizing agent. Now, if you really want to calculate the oxidation number of manganese in permanganate, oxygen is -2. There are 4 of them. That's -8. This has a -1 charge. Therefore, this is +7. +7 is going to manganese in the product side of +2. So therefore, it is becoming less positive. Therefore, it's gaining electrons and is being reduced, and therefore is the oxidizing agent. You can do that. But it's a lot easier to look at the aluminum side and say, yo, that's being oxidized, therefore it's the reducing agent, therefore the other one has to be the oxidizing agent. Now it's time to talk about balancing redox reactions. And the way we do this is to split the reaction into 2 half reactions, one of which will be the reduction half reaction and the other the oxidation half reaction. And then I've created a little mnemonic. This is pure Dr. Frank. Been using my mnemonic for years and years. Bohe equals plus. Bohe equals plus. And what the hell is that all about? Okay, so B means balance the species being oxidized or reduced on both sides of the half reaction. Secondly, the O refers to oxygen. Balance it by adding water to the oxygen deficient side. Third, for the H, that refers to hydrogen. Balance it by adding H plus to the hydrogen deficient side. And the E refers to electrons. Balance the charges by adding electrons to the electron deficient or more positive side. Then equals, find the smallest common number to make the electrons being lost on the oxidation side and gained on the reduction side equal, and multiply half reactions by a factor so the number of electrons lost equals the number of electrons gained. Then add the half reactions. The electrons should cancel out. And then check your work to see that atoms and charges balance. So now we're going to balance the reaction of chromium 3 ion plus chlorine gas, forming the dichromate ion 2- plus chloride ion. And we'll use our Bohe equals plus mnemonic to help us. First, we got to split this into half reactions. That would be the chromium ion going to dichromate and the chlorine gas going to chloride ion. Very important. Now, the next step, balance the elements undergoing redox on both sides. This step is easy to forget because the elements being oxidized or reduced are balanced on both sides. But here they're not. We have 1 chromium ion on the reagent side and 2 on the product side. And the same thing for the chlorine. We have 2 chlorine atoms on the reagent side, only 1 on the product side. So we have to balance the elements undergoing oxidation or reduction. That means we put a 2 in front of the chromium 3 ion and a 2 in front of the chloride ion. Very important step. If you don't do it, you'll have a really difficult time getting to the balanced equation. Okay, O in Bohe equals plus. O means balance the oxygen by adding water as required. So we have 7 oxygen on the product side. We don't have any oxygen on the reagent side. We're going to add 7 H2O. Now we have 7 oxygen on the reagent side, balancing 7 oxygen on the product side. We don't have any oxygen over in our chlorine half reaction. We don't need to worry about it. Balance hydrogen by adding hydrogen ion as required. So we have 14 hydrogen on the reagent side. We don't have any on the product side. We're going to add 14 H plus to the product side. Now 7 times 2 is 14 hydrogen on the reagent side and 14 hydrogen ion on the product side. Again, we don't have to do anything with the chlorine. Electrons. We balance the charge by adding electrons to the more positive side. So here are our 2 half reactions, and we have to figure out the charge on both sides for each one of these half reactions. On the chromium, we have 2 times plus 3, or a plus 6 charge. Over here, we have 14H plus and a 2 minus. So that's a total of plus 12 on the product side. Plus 6 and plus 12. For the chlorine, we have 0 on the reagent side and then a 2 minus on the product side. So what are we going to do? We're going to add electrons to the more positive side of each half reaction to get the charges to balance. So what I'm doing is adding 6 electrons to the product side on the chromium dichromate reaction, then 6 negatives and a plus 12 charge gives us a plus 6 charge, balancing the plus 6 charge on the reagent side. For the chlorine chloride, we add 2 electrons to the reagent side, and now we have 2 negative on the reagent side and 2 negative on the product side. So what do we do next? Bohe equals. We multiply the half reactions by a factor, so the number of electrons being lost in the oxidation equals the number of electrons gained in the reduction. So here we have 6 electrons being lost, 2 electrons being gained in the chlorine chloride half reaction. We multiply the chlorine chloride half reaction by 3, and that gives us equal numbers of electrons being lost and gained in the 2 half reactions. Now it's pretty simple. We just add the 2 half reactions. The electrons are going to cancel out because we'll have the same number of electrons being lost as being gained, and we just add them up to get our full balanced equation. Now we have to check that the charges balance and the atoms balance. We have 2 chromium on the left, 2 chromium on the right, 14 hydrogen on the left, 14 hydrogen on the right, 7 oxygen on the left, 7 oxygen on the right, 6 chlorine on the left, 6 chlorine on the right. The atoms balance. What about our charges? 2 times 3 plus is 6 plus on the left, and on the right we have a 2 negative, a 6 negative, that's 8 negative, and 14 positives. Add those together, that's a 6 plus on the right. So the charges balance, the atoms balance, and we're done. So let's see if you can balance this reaction. Hydrogen ion plus permanganate ion plus aluminum metal yields aluminum ion plus manganese ion plus H2O. Turn your playback off, go through your Bohe equals plus steps, and come up with a balanced reaction, and then come back to the video and check your work. Okay, here's the balanced reaction. 24H plus and 3 permanganate and 5 aluminum metals yields 5 aluminum ions plus 3 manganese ions plus 12 waters. Now sometimes you will get an unbalanced reaction that occurs in a basic solution with hydroxide instead of an acidic solution like hydrogen ion. So what are you to do? Well, solve it just like in acid media, just like we have with Bohe equals plus, and then add a last step. You add the moles of hydroxide ion equal to the moles of hydrogen ion to both sides of the equation. And then you convert H plus and OH minus, which will be on one side of the equation, into H2O. And then you simplify that, and you've got it in basic solution. So turn your playback off, try it, go through the Bohe equals plus steps. I suggest taking out water and hydroxide and adding those through the Bohe steps, and then adding hydroxide ion onto both sides equal to the amount of hydrogen ion that you have, converting that to water and simplifying. Turn your playback off, try it, and come back. Okay, here we go. Here's our balanced reaction in acid media using Bohe equals plus. Now what we're going to do is add 8 hydroxide to both sides. Now watch what happens. 8H plus 8OH minus turns into, ta-da, 8H2O. So now we have 8H2O on the reagent side and 4H2O on the product side, so we can simplify it to our final reaction. 4H2O plus 6I minus plus 2 permanganate yields 3 iodine plus 2 manganese dioxide plus 8 hydroxide. And if you check it, your atoms are going to be fine and your charges are going to be fine. Now it's time to start talking about electrochemical cells. Electrochemistry is the study of redox reactions, oxidation-reduction reactions that produce or require an electric current. The conversion between chemical energy and electrical energy is carried out in an electrochemical cell. Spontaneous redox reactions take place in a voltaic cell, also known as a galvanic cell. Non-spontaneous redox reactions can be made to occur in an electrolytic cell by the addition of electrical energy. What would happen if we took a piece of zinc metal, a strip of it, and put it into a solution of copper 2 sulfate? Well, within a very short amount of time, we'd see black copper forming on the surface of the zinc metal. And if we analyze the solution, we would find zinc ion floating around in the solution. Here's what's happening. Copper ions, copper plus 2, approach the zinc metal surface. A pair of electrons on an atom of zinc are captured by the copper ion, reducing it and forming copper metal. Meanwhile, the atom that lost the 2 electrons is now an ion and dissolves into the solution. So in the previous slide, we saw that the electrons transferred from the zinc atoms directly to the copper ions, reducing them. What would happen if we separated the process so that we could tap the energy of the electrons migrating and make them do a little electrical work? Well, that's what we have here in this electrochemical cell. We have a zinc solution and a strip of zinc metal. And over here we have a copper nitrate solution and a strip of copper metal. We have a salt bridge to connect them because ions form as this redox reaction proceeds, and they can't be allowed to build up in either of the solutions because it would stop the reaction. The electrons are now migrating from the zinc metal through a wire, and they're made to do a little work by turning this light bulb on, continuing their migration to the reduction of the copper ions in the copper half cell. So, what half reaction occurs at the anode? This is called the anode, where oxidation occurs. Zinc metal is losing 2 electrons to become zinc ion. And the half reaction is zinc solid yields zinc ion plus 2 electrons. Meanwhile, reduction is happening at the cathode, where copper ions are gaining 2 electrons to become copper metal. The reaction is Copper ions plus 2 electrons yields copper metal. Oxidation occurs at the anode. Reduction occurs at the cathode.
This is how the battery works. At the zinc electrode, each atom of zinc that ionizes releases 2 electrons. The zinc ion enters the solution, and the electrons migrate through the wire where they can do work, such as light a flashlight or turn an electric motor. Here, the electrons are causing a voltage to be registered on the voltmeter. The electrons continue on to the surface of the copper electrode, where they attract a copper-2 ion from the surrounding solution. The copper ion takes on 2 electrons and becomes an atom of metallic copper. The copper atom plates onto the copper electrode. Because positive charges would build up in the zinc solution and negative charges would build up in the copper solution, a salt bridge is needed. Negatively charged sulfate ions can migrate through the salt bridge from the copper solution to the zinc solution to keep the total ionic charges balanced in both solutions.
Here's a listing of substances from the strongest oxidizing agent, a compound that loves to take on electrons, and as we go down the list we get to the weaker and weaker oxidizing agent until we end up at lithium ion, which really doesn't want to pick up an electron very much at all. Conversely, on the other side of the half reaction, we have the reducing agents. And if something is a very strong oxidizing agent, then after it has gained electrons, it's going to be a very weak reducing agent. It doesn't want to be oxidized, and it doesn't want to give up its electron. As we go down the list, we get to stronger and stronger reducing agents, until at the very bottom we have lithium atom, which is in the list the strongest reducing agent. Now you notice these voltage potentials here. These are called reduction potentials, and they're all measured against the hydrogen ion hydrogen gas half reaction. They use a special electrode for gases, and they bubble hydrogen gas in through a small opening. The gas travels down and hits a platinum plate submerged in 1 molar hydrochloric acid. So this is the hydrogen electrode, and all of the voltage potentials that you see here are measured against this hydrogen half reaction. That's why it's given a reduction potential of 0. Cell potential. The difference in potential energy between the anode and the cathode in a voltaic cell is called the cell potential. The cell potential depends on the relative ease with which the oxidizing agent is reduced at the cathode and the reducing agent is oxidized at the anode. The cell potential under standard conditions is called the standard EMF, signified with an E0 meaning standard conditions for the cell. That means 25 degrees Celsius and 1 atmosphere for gases and 1 molar concentration for solutions. We get the standard EMF, the cell potential, when we add up the potentials for the 2 half reactions involved. So let's try this question. Which is the stronger reducing agent and stronger oxidizing agent for this reaction of tin plus 4 plus aluminum metal yields aluminum ion plus tin plus 2? Well, first we identify on each side which is the reducing agent and which is the oxidizing agent. And if we look at tin plus 4 over here and tin plus 2, it's clear that it's gaining 2 electrons. Gain of electrons is reduction, which makes it an oxidizing agent. Conversely, that means that aluminum has to be a reducing agent. And it is. Look, it's going from aluminum to aluminum plus 3. It is losing electrons. It is being oxidized. Therefore, it is a reducing agent. Going in the opposite direction, we flip it around. Aluminum plus 3 goes to aluminum metal. That makes it an oxidizing agent, and it makes the tin plus 2 a reducing agent. Now, which one is stronger? Let's compare the 2 oxidizing agents, tin plus 4 and aluminum plus 3. We find these ions in the table. Tin plus 4 is here, aluminum plus 3 is down here. And as you go from the bottom up, the oxidizing agents get stronger. Down here is the weakest oxidizing agent. As we move up, they get stronger and stronger. So tin plus 4 is a stronger oxidizing agent than aluminum plus 3. That means the stronger oxidizing agent and stronger reducing agent are on the reagent side, and the weaker oxidizing agent and weaker reducing agent are on the product side. Now, the reaction always flows spontaneously from the stronger oxidizing agent and stronger reducing agent to the weaker oxidizing agent and reducing agent. Always goes from stronger to weaker. So if we locate these ions in the table, we see that the tin plus 4 is on the upper left, the aluminum metal is on the lower right, and when you have the species involved in that configuration, upper left, lower right, you will get a spontaneous reaction. So for this, the reaction is going to flow from the reagent side to the product side as written. Now, how do we calculate the voltage of this redox reaction? Let's write down the two half reactions involved. Tin plus 4 plus 2 electrons yield tin plus 2. That's a reduction potential of 0.13. And aluminum plus 3 electrons yields aluminum. That's a reduction potential of minus 1.66. Now, one of these has to get flipped into an oxidation. You can't have two reductions forming a reaction. One of these has to be flipped to an oxidation. And the one that's going to get flipped is the aluminum plus 3 aluminum half reaction, because the reaction will flow from the stronger reducing agent and stronger oxidizing agent to the weaker reducing agent and weaker oxidizing agent. So we're going to flip this bottom half reaction around, and when we do so, we change the sign of the reduction potential. It's now an oxidation. So what was before minus 1.66 is now plus 1.66 when we turn it into an oxidation. To get the voltage of the entire reaction, we simply add these potentials, the reduction potential for the tin, the oxidation potential for the aluminum. Now, of course, when we write this as a balanced equation, we're going to need to multiply this top reaction by 3 for each term and the bottom reaction by 2 for each term to make the numbers of electrons being gained and lost the same. But here's the thing, we do not multiply the voltages by 2 or 3. We just add them as is, because the voltage potential is intrinsic to the species. Its desire for electrons, desire to give up electrons, that's intrinsic and is not based on the number of atoms of that species that we have. So we do not need to multiply our potentials here by any term we need to make the numbers of electrons being lost equal to the number of electrons being gained. So the answer would be plus 1.79. Now let's try building a reduction potential series. Given the following redox reactions with hypothetical elements, construct a reduction series and then identify the strongest reducing agent of these hypotheticals. So the first reaction is Q2 plus L yields L2 plus Q. Second one is G2 plus L yields no reaction. So let's take a look at this first one and write each one of these as a reduction. The Q2 plus 2 electrons going to Q, and the L2 plus gaining 2 electrons going to L. That means that the Q2 plus would be the stronger oxidizing agent, L2 plus would be the weaker oxidizing agent. Over on the right side, Q would be the weaker reducing agent, L the stronger reducing agent. Now remember that it's always spontaneous when the stronger oxidizing agent reacts with the stronger reducing agent, upper left, lower right. And that's exactly what we have here. Q2 plus L, Q2 plus L. Now, what about this G2 plus L? What do we do with it? Well, that means if G2 plus L yields no reaction, G2 plus has to be below the L2 plus reduction, because then G2 plus L means lower left, upper right, and that is going to give a negative overall cell potential, and no spontaneous reaction is possible. Suppose we add voltages to each one of these now, and it wants us to calculate the voltage potential for this first spontaneous reaction, Q2 plus L yields L2 plus Q. Which one of these is it going to be? All right, the L2 plus L half reaction is going to flip around so that L will be on the reagent side. When we do that, flipping, we get minus 1.21 instead of plus 1.21 when we write it as an oxidation. And then if we add these two, we will get the desired spontaneous reaction. So it'll be plus 1.55 added to minus 1.21. So that looks like a 0.34 overall cell potential. Now for G2 plus L, we know this is going to be a non-spontaneous reaction. We have to flip this middle reaction around because L has to be on the reagent side. So that is going to make it a minus 1.21 added together with minus 0.74. So that's going to be a very negative 1.95 and not a spontaneous reaction.